Hello everyone, welcome back to our Step to Engineer channel. Today's video topic is about MAWP, which stands for Maximum Allowable Working Pressure. So, we'll be explaining in detail how MAWP exists in the world of pressure vessels and heat exchangers, why it's important, and how these MAWP values are calculated. So, for designing a pressure vessel, we have specified design temperature and design pressure values. We start designing based on the requirement that the pressure and temperature must be able to withstand these specified values. Then, during the design process, there are instances where the thickness used exceeds the required value based on the specifications. In such cases, where extra thickness is used, the vessel becomes capable of withstanding pressures higher than the initially specified design pressure. For example, at a design pressure of 10 bar, the required thickness might only be 12 millimeters. However, due to market availability or other environmental factors, there are cases where we end up using a greater thickness than required. For example, if the required thickness is 12 millimeters but we can easily purchase 16 millimeters, and we end up using the 16 millimeters, then, when reconsidering the situation, the vessel will be able to withstand pressures higher than the design pressure of 10 bar due to the increased thickness. In such a situation, the pressure that the vessel can withstand due to the increased thickness is considered as the maximum allowable working pressure, MAWP. This is the maximum pressure that each individual component can safely handle, and we can calculate it based on the thickness used. Since we have the technical information and design references, let's continue by reviewing the slides. The slide we're currently viewing is a design data sheet for a pressure vessel, which contains the design information for the vessel. Well then, let's take a look at the design information of this vessel. Firstly, the most important factors, which are the design pressure and design temperature. So, the design pressure of this vessel is currently 10 bars, and the design temperature is 120 degrees Celsius. If we talk about the vessel's diameter, it's the major ID. The major ID is 3,300 millimeters. Another point is the material of the actual major component. The shell and head are to be made of SA516 grade 70 as requested by the client. So, in the second slide, we can see a PV Elite model that we created in PV Elite based on the information from the vessel datasheet. So, the design information we previously presented, such as the design pressure of 10 bars and the design temperature of 120 degrees Celsius. Another point is that the diameter is based on the ID, and the inside diameter is 3,306 millimeters. So, one thing to mention here is that the datasheet specifies 3,300 millimeters, but why did we input 3,306 millimeters here? It's because, although this vessel uses a carbon steel shell body, the client requested an additional 3 millimeters of stainless steel cladding or weld overlay for the internal surface. Therefore, when we performed the design calculations, we considered the diameter with the cladding excluded, so we added +3 and input the value as 3,306 millimeters in our calculations. So, after considering the 3 millimeters cladding, our final ID will still be 3,300 millimeters, as requested in the datasheet. Therefore, the material used is SA516 grade 70, as requested by the client. Therefore, based on the current design temperature, design pressure, and the vessel's ID, we have currently selected and chosen a nominal thickness of 19.05 millimeters and a finished thickness of 19.05 millimeters. So, to explain, based on the design information, design ID, and selected material, we have chosen a thickness that is greater than the required thickness. Now, let's take a look at the next slide. In this slide, we can see the material properties of SA516 grade 70, which we have currently selected and are using. So, the current 516 material's ambient condition and operating condition. The ambient condition refers to the temperature of the current environment, as everyone knows. The operating condition refers to the state when the vessel is actually operating, specifically under the design temperature. So, one thing to note here is that, based on the current state of this material, the stress values for allowable stress in the ambient condition and allowable stress in the operating condition are found to be the same. If we look at the image on the right, the allowable stress of the current 516 material stays exactly the same at 137.9, without any change, from a temperature of 38 degrees Celsius up to 260 degrees Celsius. Therefore, our ambient condition can be said to range around 30 to 38 degrees Celsius, and the current design temperature is 120 degrees Celsius. Based on the grade currently shown, since it is below 260 degrees Celsius, the allowable stress will not change from the ambient condition up to 260 degrees Celsius. So, starting from 288, the allowable stress slightly decreases. Therefore, it can be concluded that as the temperature increases, the allowable stress decreases accordingly, which aligns with our current understanding. Let's continue looking at the other side. So, at this point, I will proceed to explain how we derived and connected the maximum allowable working pressure based on the previously mentioned design information. So, first of all, with the design pressure of 10 bars, the MAWP maximum allowable working pressure based on the selected thickness is 15.78. Therefore, the maximum allowable working pressure MAWP for the shell body of this vessel, which is the maximum pressure that can be safely used, is currently 15.8 bars, as we have observed. Although the design pressure is 10 bars, due to the selection of a thickness that is greater than what is required, we are seeing a situation where the maximum allowable working pressure MAWP is higher than the design pressure. Therefore, when the required thickness is 12.04, we have selected a thickness higher than required due to factors such as market availability, other environmental effects like blast loads, saddle reactions, vessel transportation, and other environmental influences. As a result, we are using a thickness that exceeds the required value based on what is available in the market. So, based on internal pressure alone, the required thickness is 12.04, whereas the selected thickness we are currently using is 19.05, as can be seen. So, let's continue to explore how the value of 15.78 bars for the MAWP of the shell main body was derived and how it came to be. In the current slide you're viewing, he will explain how the required thickness was calculated. Based on the design temperature, pressure, and vessel diameter that we entered keyed in, we will show you how the required thickness was generated and calculated. What you're seeing now is the required thickness calculation generated by PV Elite. This section and the formula used come from ASME Section 8, Division 1, under UG to 7. The formula for calculating the required thickness, which you see below, is derived from this section of the code. T equals P times R, S times E, 0.6 times P. So, what do these values and terms mean and how are they applied? So, first of all, P, which stands for joint efficiency, refers to the efficiency of the welding joint when we perform a weld. So, the details will be explained further in the upcoming videos. Continuing on, P refers to the internal design pressure, which is the design pressure value for our vessel. The next term is the inside radius of the shell, which is the radius value of the main shell body. This radius is half of the internal diameter of the vessel. The next term is allowable stress. This refers to the stress value that varies depending on the temperature, which we saw in the previous slide. The allowable stress changes with the temperature range, with different values for the minimum and maximum temperatures. So, the last term is T, which is the minimum required thickness of the shell. This is the thickness needed for the shell to safely handle the internal pressure. So, The value of 12.04 millimeters generated by PV Elite is the current required thickness. So, let's take a closer look at how this required thickness of 12.04 millimeters is calculated. So, let's manually verify the required thickness value auto-generated by PV Elite using the ASME formula. So, for the given information, the design pressure for this vessel is currently 10 bars, and the inside radius is derived by dividing the vessel diameter by 2. Additionally, the maximum allowable stress value, based on the current design temperature, is within a consistent range and remains at 137.9 in per square millimeter. According to the formula, we will convert the stress value to 1379 bar and use a joint efficiency of 1. So, using these imported values and applying the formula, we can see that the required thickness of 12.04 millimeters is obtained. So, when we compare the value generated by PV Elite with the one calculated using the formula, we find that both values match perfectly. So, at this stage, we have calculated the required thickness based on the imported information. So, to determine the MAWP maximum allowable working pressure, we can use the formula based on the given thickness of 19.05 millimeters. Vessel diameter, maximum allowable stress, and joint efficiency. By applying the formula, we can reverse calculate the MAWP. Actually, ASME Section 8 already includes a formula to calculate the MAWP. PSET, or plus 0.6 T. So, by using the input information, when we calculate the maximum allowable working pressure MAWP, we get a value of 15.78 bars, which matches the value generated by PV Elite. So, what I want to highlight here is that we have calculated the required thickness based on the imported information. In reality, more than 12 meters is required. However, due to other environmental effects and various requirements, we ended up using a higher effect value for the application. Additionally, based on the available thicknesses in the market, we have used what was accessible. So, the thickness we used is noticeably higher than the required thickness. There were specific circumstances that led us to use this increased thickness. So, if we were to reverse the calculation, we would determine how much pressure this vessel can withstand based on the thickness we used. This involves applying the formula to calculate the pressure that the vessel can handle using the thickness we have selected. For 10 bars, 12 millimeters thickness is required. If we use 90 millimeters, we calculate the pressure the vessel can withstand, which is the maximum allowable working pressure MAWP. So, at 10 bars, a thickness of 12.04 millimeters is sufficient. So, with a thickness of 19.05 millimeters, the vessel can withstand up to 15.78 bars. While the design pressure is 10 bars, with this thickness, the vessel can handle up to 15.78 bars. The vessel, as a whole, can withstand it, and this is evident. So, based on the thickness of the shell main body, the MAWP is 15.78 bars. So, not only the shell body but also other components like individual components, heads, flanges, nozzles, and tube sheets of the heat exchanger need to be considered. Each component's MAWP is calculated using the relevant methods. Finally, the overall MAWP of the entire vessel is determined by reviewing and combining all these values. At this stage, we are clearly calculating and verifying the MAWP of the major component, which is the main body of the vessel. Thank you for the clarification, and I appreciate your time. A big thank you to everyone at Step 2 Engineer channel for the support.